So we are doing our last lecture, the first part. Now we talk about solution of heat conduction problem. So the basic equation we consider heat conduction equation. So the conditions are, we have a metal rod along the x-axis lying between the positions x equals 0 and x equals L. We have the ends x equals 0 and x equals L are kept at constant temperature 0. The lateral surface is insulated. So heat flow is through the ends. So under these conditions, and we have the initial condition, initial temperature distribution is known. Is given. So under these conditions, the basic equation, so U xt is the temperature at position x at time t. So our main equation, partial derivative of the temperature function with respect to time, is equal to some positive constant alpha squared times the second partial derivative with respect to x. The ends x equals 0 and x equals L are kept at constant temperature 0. So these are called boundary conditions. When x equals 0 or L, at all times the temperature is 0. And so these are called, these are boundary conditions. And the initial temperature distribution means when we take time t equals 0, initially, we know the temperature at every point x. So it is given by a function of x. So far, what we did is we get the solution of the part where we consider the equation with boundary conditions. So we have seen that the function uxt defined as an infinite sum, n from 1 to infinity, some constant cn times the exponential function e to the power minus alpha squared n squared pi squared t over L squared times sine of n pi x over L. This function satisfies the equation ut equals alpha squared uxx and boundary conditions u0t and ult are 0. Okay, so now in order to find our solution, we need to find the constants. Now we find constants Cn by using the initial condition. Ux0 is given by this function f. On the other hand, we know that u is given by this infinite sum. So in this sum, if we take t equals 0, we have e to the power 0, which is 1. So we have the infinite sum, n from 1 to infinity, Cn times sine of n pi x over L. So we get, let me say that initially this function is defined for x between 0 and L. So we need to write this given function, initial temperature distribution function, f, as this infinite sum. And we have seen how to do that. This series is called Fourier sine series. In the previous lecture, we have seen how to find the constants. So the constant in front of the sine part in the Fourier, this is the sine series, the Cn in general from the definition is given by 1 over L times the integral from minus L to L f of x sine n pi x over L dx. Okay, now our function here is only defined for x from 0 to L. It is not defined for the interval from minus L to 0. So, but we know that it is given by this infinite series, Fourier sine series, and sine function is an odd function, and infinite sum, this is going to be an odd function. Although if it's not defined for negative numbers, this doesn't make much sense, but we use this to find, to rewrite this integral. So we consider the function f of x as an odd function, since it is given by a sine, since it is given by a Fourier sine series. So this integral, Cn is equal to 1 over L, integral from minus L to L, f of x sine n pi x over L. So f is an odd function, sine is an odd function. So when we multiply them, we get an even function. So for the even function, the integral from minus L to L is twice the integral from 0 to L. So this is the integral we are going to use for the constants, constant Cn's. Okay, let's look at an example. Find the solution of the heat conduction problem uxx equals ut for x between 0 and 40, t positive. Boundary conditions u0t and u40t, they are 0 for all t positive. And the initial condition at time t equals 0, the heat distribution is given by the function defined to be x if x is between 0 and 20, and 40 minus x if x is between 20 and 40. Okay, so of course, if you just take this question, you need to do all the steps we did in lecture 25. You apply the method of separation of variables. You obtain a pair of ordinary differential equations. And using the boundary conditions, you obtain the boundary conditions for one of those equations, find the solutions, find the values. Remember, if you remember that lecture, we need to find the value of some constant lambda, which gives us non-trivial solutions. And then combining those solutions, we obtain this solution. I just give you the result here. We obtain this solution. Okay. Of course, this is under the assumption that the ends, the boundary conditions are both 0. Otherwise, if the boundary conditions, we are going to consider in the second part of this lecture, we are going to consider some other possibilities for this heat conduction problem. But under these assumptions that boundary conditions are 0, and the initial temperature distribution is given by the function f, we know that let's identify the parts of the solution from the given problem. The constant alpha square is 1 in this problem because uxx is equal to ut. So alpha square is 1. The length of the rod, x is between 0 and 40, so the length L is, the number L is 40. What else do we need? I think that's all. So we know that U is given as this infinite sum, n from 1 to infinity, Cn e to the power minus alpha squared is 1, n squared pi squared t over L squared. So 1600 times sine of n pi x over L. L is 40. And the constants, Cn's, are given as 2 over L, which is 40, times the integral from 0 to 40, the function f of x times sine n pi x over 40 dx. Okay, so to find the constants, now we need to figure out this integral. F is given with 2 different formulas for x between 0 and 20 and between 20 and 40. So we need to break this integral up to 2 parts. So we continue, Cn is equal to 2 over 40, so it's 1 over 20. First, we take the integral from 0 to 20. And in this interval, the function f is equal to x. And then we take the interval from 20 to 40. And in this interval, the function f is given as 40 minus x. So we need to figure out the value of this integral. So in both integrals, we need to figure out x times sine n pi x over 40. So let me call this I, integral of x times sine n pi x over 40. Let's find this out separately, and then we can use it to evaluate this constant Cn. Okay, so for this integral, we use integration by parts. We call x as u and the remaining part as dv. So du is dx. And v is ni derivative, so minus 40 over n pi. N is a fixed number here now. We are trying to figure out the constant Cn, so we fix an n, an integer, greater than or equal to 1. So n is constant here. We are doing the integration with respect to x. Cosine n pi x over 40. So the integral I is equal to u times v minus 40 over n pi x cosine n pi x over 40 minus the integral v du. So minus, this becomes plus 40 over n pi cosine of n pi x over 40 dx. So let's take out 40 over n pi. We have minus x cosine n pi x over 40 plus ni derivative of cosine is sine. But first we need to divide by the coefficient of x, 40 over n pi, sine of n pi x over 40. Plus c, of course, but since we are going to evaluate definite integral, that c part is not important. So if we want to take the integral from 0 to 20 of x sine n pi x over 40 dx, it is going to be this thing. Let me rewrite here. And we take x from 0 to 20. So if we take x equals 20, 20 over 40 becomes 1/2. So minus 20 cosine of n pi over 2 plus 40 over n pi sine of n pi over 2. Okay, and then minus, if you substitute 0, you see the first part, x cosine, since I use x equals 0, that part is going to be 0. The second part, when x is 0, we have sine 0, so minus, it's going to be 0. So I can take out a 20 here. So this is 800 over n pi minus cosine n pi over 2 plus 20 over, 2. I'm taking out 20, so this is plus 2 over n pi sine of n pi over 2. Okay. Now I need to figure out the integral from 20 to 40 of minus x times sine n pi x over 2. So there's some, well, okay, let's take this minus sign into account later. Okay, so let's figure out the same integral now from 20 to 40. Maybe we can't do it now. So now we do the same thing, but now from 20 to 40. So this is, let me write the function first. From 20 to 40. Okay, so first we substitute 40. So minus 40 cosine n pi plus 40 over n pi sine of n pi. One of them is going to be 0. Sine of n pi is 0, right? So at multiples of pi, sine function is always 0. Cosine n pi sometimes is 1, sometimes it's minus 1, depending on whether n is even or odd. So let's leave it that way. Then minus, we take x equals 20. So minus, another minus, it becomes plus 20 cosine n pi over 2. Minus 40 over n pi sine of n pi over 2. Okay. Now we have one more integral. Let's see, what was the integral? Let's see if I can write it here. We also have this integral. So this is one integral. Now the last one, we have from 20 to 40, 40 times sine n pi x over 40. So this is equal to 40 is constant. Antiderivative of sine is minus cosine. So minus 40. Then I take 40 over n pi cosine of n pi x over 40 from 20 to 40. So this is minus 1600 over n pi cosine of n pi minus cosine of n pi over 2. Okay, so let's put everything together. Then the constant Cn, the first integral, where's my first integral? Here, 800 over n pi minus cosine n pi over 2 plus 2 over n pi sine n pi over 2. Let's see if I can remember this. 800 over n pi minus cosine of n pi over 2 plus 2 over n pi sine of n pi over 2. Did I do this right? Minus cosine n pi over 2 plus 2 over n. Yes. And then we have this integral, right? Plus the integral from 20 to 40, 40 sine n pi x over whatever. So minus 1600 over n pi cosine of n pi minus cosine of n pi over 2. And then we have this with a minus sign. So minus 40 over n pi minus 40 cosine n pi plus 20 cosine n pi over 2 minus 40 over n pi sine of n pi over 2. Okay, let's see. We have cosine of n pi over 2 here, here, here. Let's combine the coefficients. I have minus 800 over n pi here, plus 1600 over n pi here. So I have plus 800 over n pi and minus 800 over n pi. So these terms cancel out. The coefficients cancel each other out. The sum of these two minus 1600 over n pi, and then this one plus 1600 over n pi, so they cancel each other out. Wait, not this one. I'm sorry, not this. This one. These two gives us minus 1600. Okay. All right, cosine n pi, I guess they also cancel each other out. This is minus 1600, this is plus 1600. So let's do it with double bars. These two also cancel out. So I'm left with sine n pi over 2. And the coefficient here is 1600 n squared pi squared. And same thing here. 1600. Okay, 3200. Did I forget a 1/2 somewhere? Oh, yes, I forget to write 1/20, right? In front of Cn, I have 1/20. I forgot to write this one, right? So Cn, 1/20 times all this. Okay, there's a 1/20. So I have 1600 plus 1600 divided by 20. Okay, so 1600 over 10, 160. So this is 160 over n squared pi squared sine n pi over 2. So after all this long computation, Cn comes out to be this simple expression. Okay, so what is sine of n pi over 2? That depends on n, of course. Let's now we can analyze this further. So let me rewrite Cn. So Cn is 160 over n squared pi squared sine n pi over 2. Now, first of all, when n is even, it's going to cancel out with the 2, so you're going to get a multiple of pi, and we know that at multiples of pi, sine is 0. So we know that this is going to be 0 if n is even. If n is odd, then we get a multiple of pi over 2. So that's sometimes 1, sometimes minus 1. So if n is odd, so if n is like 2k plus 1 odd, okay, let's see. If n is 1, meaning this number k is 0, then sine pi over 2 is plus 1. But if n is 3, so when k is 1, when n is 3, sine of 3 pi over 2 is minus 1. So this is going to be, we have minus 1 to the k times this coefficient. If n is given as 2k plus 1. So instead of n squared, I should write 2k plus 1 squared. Okay. All right, so in the sum, our function u x t, remember, is the sum n from 1 to infinity, cn e to the minus n squared pi squared t over 1600 times sine n pi x over 40. In the sum, when n is even, the coefficient is going to be 0. So there is going to be no term coming from even n. So only for odd n, and n depends on k, we can write the sum on k. K starts from 0 to infinity because n starts from 1. So k starts from 0. We have the coefficient c, 2k plus 1, given as minus 1 to the k, 160 over 2k plus 1 squared pi squared. E to the power minus, for n, we take 2k plus 1. Okay. So this is the solution of the given heat conduction problem. Now, it is an infinite sum, so how do we know that it is convergent? For convergence, we refer to the Fourier convergence theorem, whose proof is beyond the scope of this course, so we are not going to talk about that. We just accept the Fourier convergence theorem, and according to that theorem, when the function f and its derivative are piecewise continuous and periodic, then this series converges. Our function f is only given on the interval 0, 40, but for the convergence purposes, we consider it to be extended as a periodic function beyond 40. So we can consider this as the Fourier series, and we know that it is convergent. One thing I want to point out here, for this problem, for any problem of this type, so for this heat conduction problem, I mean the problem where with 0 boundary conditions. on the boundaries, the temperature is kept at 0. When you take the limit as t goes to infinity of this temperature function, okay, the constants are affected by the number L and the number alpha squared, but they don't affect, doesn't matter what alpha squared and what L is, you always have a negative exponent for E and the sine function. Now the sine function is bounded, doesn't matter what the coefficients of x are. Sine function is always between -1 and 1, and Cn is just some constant depending on n, of course. But if you consider each term separately, for each n, this coefficient is constant, and the exponential part, as t goes to infinity, you see it's always negative, because we have L squared, alpha squared, pi squared, n squared. So all of them are positive with a negative sign in front. So as t goes to infinity, this exponential part will go to 0, and this function will always go to 0. And when you consider the physical situation, this is logical, because you keep the n's constant at 0. And the heat is escaping through the ends. So as time t goes to infinity, all the heat is going to escape through the ends. And since the ends are kept at constant temperature 0, the whole temperature of the rod at every point is going to be 0 eventually. Okay. Now, let me do just one more example here. In that example, the evaluation of the constants is going to be much more simple. I want to show you that kind of an example. So example 2. So basically the same question, find the solution. So what are the parameters? Alpha squared, we need to know what alpha squared is, what L is. For alpha squared equals 1/4, L equals 2. And of course, we need to know the initial condition. The initial heat distribution is given by the function. Let me rewrite it down here. The function f of x is given by 2 sine pi x over 2 minus sine pi x plus 4 sine 2 pi x for x between 0 and 2. Okay, so we know that the solution is given by the sum n from 1 to infinity Cn e to the minus alpha squared, that's 1/4, n squared pi squared t over, because of alpha squared, I have a 4 in the denominator, and I also have L squared in the denominator, which is 4, so 4 times 4 is 16, as sine of n pi x over L, which is 2. And when I put t equals 0, I need to get the function f. For the series, when I put t equals 0, exponential part becomes 1. So Cn of sine n pi x over 2. The thing is, here the function f itself is given in terms of sine functions. So all we need to do is compare the coefficients. So the first part, so this function should be, the function f of x is 2 sine pi x over 2 minus sine pi x plus 4 sine 2 pi x. So this means in the series, we have only 3 terms, okay? This term, the first term, n pi x over 2, pi x over 2, so it corresponds to n equals 1. This term corresponds to get pi x, n equals 2. And this term corresponds to get 2 pi x, corresponds to n equals 4. Okay? So for n equals 1, the constant C1 should be here, the coefficient in terms of sine pi x over 2 is 2. So the constant C1 is 2. And for n equals 2, constant C2 is minus 1. The coefficient of sine pi x is minus 1. And the coefficient of sine 2 pi x is 4. That means C4 is 4. And all others are 0. Because the function f itself is given in terms of sine functions. Okay? So that means our solution has only 3 terms. For n equals 1, C1 is equal to 2. So if I take n equals 1, e to the minus pi squared t over 16 sine pi x over 2. And for n equals 2, this constant C2 is minus 1. So this is n equals 2. E to the minus 2 squared is 4. So that 4 cancels with the 16. Pi squared t over 4 sine pi x. And then for n equals 4, C4 is 4. E to the minus n squared is 16, so 16 and 16 cancels out, pi squared t sine of 2 pi x. This is the solution. Okay, so for basically, we know the general form of the solution. It has 2 parameters, the number alpha squared and the number L. Afterwards, to find the constants, we need to know the initial heat distribution, the initial condition, the function f of x. And using this function, we just figure out the coefficient Cn and obtain the solution of the problem. Okay, now for this, in the second part, in the next part, I'm going to consider again the same equation, but with different boundary conditions. Of course, this is only a very small part of partial differential equations. There may be any kind of equations, even coming from physics. There is the wave equation, other heat equations, other type of physical situations, all kinds of equations. But the method of separation of variables, if you can apply it, if you look at the exercises in the book, there are some exercises for you to see whether you can use the separation of variables or not. Sometimes you can, sometimes you can't. If you can, then you obtain a pair of ordinary differential equations, and for one of those equations, you use the boundary conditions to obtain your boundary conditions, and you try to find non-trivial solutions of that equation. And combining those equations, those solutions, we try to write an infinite series for the solution of the partial differential equation. So for different equations, you may end up with different pair of equations, different non-trivial solutions. If you keep reading the book, it covers some other cases, but in the next part, I'm just going to cover 2 more cases, and that's going to be all for this course. Okay, so we stop here for the first part.